Hey guys, in this video, we're going to talk about section 6.1 some more. This is part B of that lesson. If you missed the beginning of it, of us talking about what vectors are and how we notate them and find magnitude, then please go back and watch part A. This is going to pick up with using vector operations. So you already need to understand how vectors are formed and written and notated. So make sure you go watch that other video before watching this one. Okay, so vector operations, you're going to see that there's two main ones that we're going to focus on. One is vector addition and the other is scalar multiplication. Okay, so when you have like two or more vectors, if you wanted to add the vectors together, what you're going to do is add their horizontal components and add their vertical components. That's what you see right here. So if I was going to add the vectors u and v, right? Here's what u is, there's what v is. What you're going to do is you're going to add their horizontal components to get the new one and add their vertical components to get the new one there. Okay? So there's all there is to that. Now, scalar multiplication, what scalar means, we got to get a definition for that. What we mean by that is it's just a real number. It's not a vector. So if I say scalar multiplication, it means I'm going to take just a plain old Jane number and we're going to multiply that times your vector. And the way that works is the exact same way distributive property works. So if you see here, if k is a scalar, it's just a real number, okay, and I multiply that through, then what I'm going to end up with is k times both of those components. And so it becomes just a distributive type of situation right in there, but it still looks like a vector in the end, okay? We still get vectors as answers with these vector operations. So we're going to go through a few examples here. You're going to see example 3 where they're asking us to add these two vectors together. Now they have defined them at the beginning up here. They said u is -1, 3 and v is 4, 7. And what we're going to do is first start off by adding them. Okay, so first thing I'm going to do is I'm going to just rewrite it a little bit. So we see u and v. Okay, the way that these get added again is combine their horizontal components. So we get -1 plus 4, and then 3 plus 7 for those vertical components. Combine these numbers, we get 3 and 10. That would be what u plus v would be. Okay? Let's look at another one. The next one is asking us to use a scalar. They said to do 3 times the vector u. So in order to calculate that, we are going to take 3 and multiply it by vector u. And u again was -1, 3. In order to do that, we are going to simply just distribute the 3 through. So this becomes -3, 9. There's all that is to that one. All right, but what if we got multiple things going on? How do we deal with it if we have more than one operation happening? And this is where I want you to keep in mind order of operations, as it has always been, PEMDAS, right? Please excuse my dear Aunt Sally. However you learned it, you need to use that method when it comes to this as well. Okay, so if you see that there's multiplication and multiplication and addition, which one are you going to use first? Multiplication, and then you will add later, okay? So we're going to go through that process right here with this guy. All right. I'm going to first of all go ahead and replace each thing. So the u, I'm going to replace that as a -1, 3. Then I'm going to replace v to be 4, 7. And then we're just going to go through it. I'm going to multiply the 2 through this first one. So that's going to give me -2, 6. We're going to distribute the -1 through here, which is -4, -7. And then we're going to combine our x's and combine our y's. So again, you can write it in multiple steps if you want. This is a -2 minus 4, 6 minus 7. So we get a -6, we get a -1. Ta-da! All right, there's that one. On to our next term. All right, this next one is where things start getting more interesting. Okay, so if you've been like, oh my gosh, this is boring, just end it now, right? We want to do something different. Here's where things start getting a little bit more interesting, is this thing called a unit vector. Zoom out a little bit. All right, the unit vector, it is a vector that has a length of 1 or a magnitude of 1. Okay. Now, I want you to think about if we try to find the unit vector of another vector, what's the purpose of it? Well, what the unit vector does is it represents the direction of any non-zero vector. So this works as long as my vector is not 0. Okay? And here's kind of the simplicity of it. The unit vector will be the original vector divided by the vector's magnitude. If you do that, you're going to end up with a vector that has a magnitude of 1, but it's going in the direction of the vector we're dealing with. Okay? All right. Let's try it. So what you're seeing in example 4 is they said, first of all, find a unit vector for v, and they said verify its length is 1. So they want us to make sure that we've done it right, okay? Because there's an easy way to check. All right, so if I want to find the unit vector for this problem, right, we're going to just use that formula. But in order to use it, I need you to think about what it is I need to plug in. For the unit vector formula, I need both the vector and I need its magnitude. So if I'm missing either one of those, I'm going to have to figure them out. So look at my problem. I do have the vector v. However, I do not see its magnitude, which means I need to take a step and I need to find its magnitude. So let's start there. All right, so if I find the magnitude of v first, let's say magnitude of v. Since they gave me the component form, then we can use the simpler way of finding the magnitude, which was using Pythagorean theorem. Here's my a, that's the -3, and then this one's my b, that 2. And so I'm going to plug those in. All I need to do is -3 squared plus 2 squared. Okay. -3 squared is 9. 2 squared is 4. This gives me the square root of 13 for my magnitude, which I could give as a decimal. I'm just going to leave it like this for the time being, okay? Because if I'm not given a good reason to give a decimal, we're just going to leave square roots. Okay, cool. So if that's my magnitude, I should be good to find my unit vector now, because the only two things I needed was my vector, which I was given, and I need the magnitude, which I found. So let's find the unit vector. The unit vector is going to be found by just dividing the two. You're going to have your -3, 2 divided by the square root of 13. And the way that's going to appear is not the prettiest thing in the world, but I would have this as -3 over the square root of 13 and 2 over square root of 13. If you needed to rationalize it, you could. I'm just going to leave it like this for now, but you definitely could rationalize it if you needed to. Okay, so if you had multiple choice answer options and you saw they're all rationalized, you could do that. But this is fine for an open answer. Okay. All right. The other thing I'm supposed to do is verify its length is 1. So this is my unit vector, but I also need to verify. So in order to verify that its length is 1, I need to find the magnitude of my unit vector, because the idea is that the magnitude is going to be 1, right? If this is truly the unit vector, make sure that the unit vector's magnitude is in fact 1. So we're going to calculate that. Again, because I've got my components here, then I can use the simpler version, although it's still going to look kind of ugly because we're dealing with fractions. So I'm going to take the a value and square that, and then the b value and square that. Negative 3 squared is 9 over the square root of 13 squared is 13. Keep in mind this is all still under the square root. 2 squared is 4 over the square root of 13 squared is 13. So we have 9 over 13 plus 4 over 13. 9 plus 4 makes 13 over 13. That is, in fact, 1. Nice job. All right. Told you to get a little bit more interesting, right? All right. Now, for it to become even more interesting, we're going to talk about direction angles, okay? This is probably going to be the last topic for this video is the direction angles. We have a couple of examples. We're going to work with them, and then we will probably call this video quits and move on to the next one. So direction angles. You see here the angle theta that V makes with the positive x-axis. If V has a direction angle of theta, then the relationship we have is right here. Now, I want you to think about it for just a moment, okay? Because, I mean, this all corresponds to some things that we've learned about in the past. So just really try to bring everything together, okay? If this is my vector, and then I'm looking at this angle theta, right? The angle theta that V makes with the positive x-axis. Where have we seen that before? We have definitely seen that pattern, making that angle with the positive x-axis, all throughout doing the unit circle and trig stuff, okay? So when I see here that it says if V has a direction angle of theta, then we have this relationship for the A and the B components. Now I want you to remember that I'm going to bring this back from our video 1, okay, video from part A. A is talking about this horizontal component, whereas B is talking about the vertical component. So I want you to think about where those values come from. This A value right here, that goes along with this X. If you were looking from here to here, that's an X, right? Remember how in trig we did the r cosine theta type of thing? R, in this case, is the length of this vector. That's the magnitude. So think about it there. Think of it compared to r cosine theta. This is the magnitude of V, which is like the r. Cosine theta, that's talking about this distance. And then the same logic to get this one right here. This is the magnitude of V. I know it's pretty little, so if you're having trouble seeing it, that's what that's supposed to say. Magnitude of V, sine of theta, is going to give me that vertical right there. So we can see the horizontal and vertical components using some of the trigs that we just got done learning about in our last unit. Okay, so from that, we have a couple examples. Number 1, we're going to do example 5, and it says to find the components of V with a direction angle 115 and a magnitude of, wait for it, 6. All right, so we are using the relationship we just had right up in here. They said find the components. They gave me the magnitude and they gave me the direction angle. So this is a simple matter of plugging things in, okay? So here we're going to see V, the vector. That's going to be our little components here where I plug it straight in. Now, if my magnitude is 6, that is what this piece in the front is, right? So it's going to be 6 times cosine of 115 degrees. That's going to give you that first component. And then we're going to do the exact same thing with just sine. 6 sine of 115 degrees. Okay, so this is something I'm good if you want to type this in your calculator and estimate it because it's not one of our special angles, right? It's definitely one of those that's trickier to calculate. So I'm going to let's say you can use a calculator to plug it in and get a decimal for this. You should end up with negative 2.536. If you are not getting that, make sure your calculator's in degrees and try it again. All right. And then for the second component, we should have 5.438. But that's the components of this vector. If it has a magnitude of 6 and that direction angle, plug and chug. Okay. Now, when it gets a little bit more interesting is this guy down here. It says that we are going to find the magnitude and direction. So this one's kind of backwards. The last one said find the components, and they gave you the magnitude and direction. This one says here's the components, find the magnitude and direction, and round to 3 decimals. In some cases, this can be very simple. In other cases, it's not as much. So we need to be very mindful of where these are positioned if you were to look at them on an axis. Okay, if you're going to look at these actually compared in like that standard form coming from the origin, where they positioned, and be careful that our trig values are actually falling in the quadrant they're supposed to. I know that's not our favorite thing, but it's something that's important to watch out for. So we're going to look here at A. Okay. And first things I said to do, find magnitude. Oh, that's easy. I've got the A and the B. I can get magnitude, no problem. We're going to plug that into the A squared plus B squared under the square root. So that's 3 squared plus 2 squared. 9 plus 4, square root 13. Now, did you notice that the answer or the direction said to round to 3 decimals? If they give you that direction to round to 3 decimals, then we have to do it, right? So I'm going to go ahead and give you what this would be. Rounding that to 3 decimal places gives us about 3.606 for the magnitude of U. Awesome. Okay, the next thing we're supposed to do is find the direction. Find the direction in degrees. I'm going to use a different color just to try to keep this a little bit more clean. But to find the direction in degrees, this is where we're going to use that relationship that we talked about up a little bit higher. Let me bring that back. Okay, right here. Remember how we said the magnitude of V times cosine of theta? That's giving you that A component. I know my A component is 3, right? So here's what I want you to think about, right? I know that that A value has to be equal to the magnitude of U times cosine of theta. That has to be true because this is representing the A value, okay? And the A value is 3. So that has to be true. So if I already found what the magnitude was, right, the square root of 3, I'm going to go back to use that because it's a little bit more specific. And I know what A is. We can plug those in. Plug in the 3. Plug in the square root of 13. And then solve for theta. What I'm going to do here is divide both sides by the square root of 3 so that I have, square root of 13. 3 over square root of 13 is equal to cosine of theta. This is where you can use your inverses, but you have to be really careful when you do this, okay? If I do cosine inverse of 3 over square root 13, that will give you theta as long as it's actually within the interval that cosine inverse calculates for. So I don't know if you guys remember back when we did this in the last unit a long time ago, but cosine inverse is always being calculated from 0 to pi. That was where we looked at it and we saw it being like, we shaded like the top of it. Okay, that's where cosine inverse exists. So I need to make sure that my angle is actually falling where it's supposed to because of that. So one thing to note You notice how here this is the vector 3, 2? Well, that means the vector 3, 2 is located, let's see, 3, 2 is probably going to be in, I don't know, we're going to say, let's go 1, 2, 3 like this, 1, 2, something like that, okay? Notice how that is, in fact, in the shaded section where cosine inverse calculates for. That means when I do this math, I will get the correct answer, and there's no issues with it. I don't have to do anything special to fix it, okay? It's when it's outside of that where it's going to be a little bit more tricky. So I'm going to go ahead and say, let's just type that part in the calculator. Cosine inverse 3 over root of 13. And if you do that, typing that straight into the calculator, you should see that theta is going to be about 33.69-ish degrees. And that's a fair estimate, okay? Because the vector where it was positioned, again, watch out for it. It is positioned in 3, 2, which is going to be in this quadrant, and that is safe for calculating cosine inverse. So here's your question, I'm sure you're thinking. What happens if it's not in the correct place? How do we deal with that, right? And so that's something I'm going to show you a little trick for how to get around it, just to kind of make things a little bit easier on yourself, okay? And that's what we're going to deal with on B. So honestly, on this one, it's the trig that's a little bit more tricky to deal with than it is the actual vectors themselves, okay? And this is my last one for this video. So just hold on tight and we'll get through it, okay? Okay. So here we're going to deal with, first of all, finding the magnitude, because that is what it says to find, right? We're going to find the magnitude of V. And just like on the last one, it should be pretty simple to solve because we do have the A and the B. Negative 2 squared plus negative 5 squared. So this should be 4 plus 25, square root of 29. And because it did say to give a decimal, we're going to go ahead and get one. This is 5.385. Okay. So we've got that. That's the magnitude. Okay. We had the magnitude back here for that one. Here's the magnitude for this guy. But now I've got to deal with the trig part. I'm going to do this in a different color because I don't think the red was showing up super duper well on that screen. Maybe that's just my eyes, but I'm having a hard time reading it on the screen myself. So I'm going to do this in green. Okay. We're going to start off the same way we started the last one. You remember how I said A equals the magnitude of U cosine theta? I'm going to start off the same way. So I'm going to still think of that. A equals, now this is the magnitude of V cosine theta. I do know A, that's supposed to be negative 2. I also know the magnitude of V, which we said was the square root of 29. So again, this is starting off the same way that the last one did. If I divide both sides by the square root of 29, this is negative 2 over the square root of 29. Then you would do cosine inverse but this is where the danger comes in, okay? Because it's not exactly this. Here's what I want you to look at. Think about where this vector is supposed to lie versus where cosine inverse should be calculating for, okay? Your calculator is using cosine inverse the same way I showed before in that top section. So I'm going to draw this smaller, but just like before, cosine inverse is calculating for up in here. But look at where this angle is. This vector is supposed to be at 2, negative 5, or negative 2, negative 5. So if I go negative 2, negative 1, 2, 3, 4, 5, I'm looking at down in here. which is not really supposed like what we're calculating with cosine inverse. So here is the trick to getting around it, because if you calculate, even if you calculate cosine inverse, you're going to end up with like 111 degrees, which you can know is not correct because I need to know this whole angle, which is more than 180. Okay. So what I want you to think about is if you do type this in, that's okay. You don't worry about it. It's fine. You'll get 111.801 degrees. But that's not exactly where we're supposed to be at. Okay? Because I need this to be actually in quadrant 3, whereas what I'm seeing right here, this is seeing quadrant 2, right? 111 degrees would actually be up in here. But I need it to be, needs to be quadrant 3. And there's actually a pretty easy fix, okay? All I need you to do is take that full 360 degrees and subtract what you just got. And it will land you where you need to be, okay? So there's a little workaround there. But there's an extra step you've got to do if it's not in the correct quadrant to begin. All right, I know this one was a little bit longer. Sorry for that, but stay tuned for the next video that I will post to wrap up this section on vectors. All right, I will see you guys in the next one. Bye.